Imagine that you're making an iced tea on a warm Sunday afternoon. You will have to pour a 1 liter pack of juice powder to a pitcher that contains 1 liter of water. And when you pour the powder into the container and shake, the powder would completely dissolve, which means the powder will become part of the water. The water with juice powder will now result to a cool and sweet iced tea.
Now, let us say you put 5 packs of juice powder instead of 1 in the same container. There would still be powder at the bottom of the container because that 1 liter of water can only dissolve a specific amount of juice powder.
That is because that 1 liter of water has a solubility. To put that in context, solubility is the amount of solute, in this case the powder, that will dissolve in a given amount of solvent, the water. Molar solubility, however, is the number of moles of solute that dissolves to give 1 liter of saturated solution. If you're wondering, a saturated solution is a solution that is unable to dissolve more solutes. Of course, not all solids can be dissolved in water. Some are very slightly soluble that they are considered as insoluble compounds. Now, how can you determine when a compound is soluble or not? Barium sulfate, for example, is an insoluble compound, and when put into water, a small amount of barium ions and sulfate ions will break away from the surface of the solid and go into solution. Over time, some of these return from solution to stick onto the solid again. This is the equation when the barium sulfate breaks down into barium ions and sulfate ions. A chemical equation has two sides: the reactant side, the side where the barium sulfate is located, and the product side, the side where the barium and sulfate ions are located. The two arrows that points in the opposite directions implies that the equation is reversible, which can go forward from the reactant side and backward from the product side. After some time, this reversible reaction will reach equilibrium. That is when the rate to form the reactants and the rate to form the products are exactly equal. Reversible reactions, or the reactions that can establish equilibrium, have their own equilibrium constants. The equilibrium constant is the ratio of the concentration of the products to the concentration of the reactants at equilibrium. In the case of the barium sulfate, the equilibrium constant when dissolving an insoluble compound in an aqueous solution is called the solubility product constant, also known as the KSP. Going back to the equation, we can calculate the equilibrium constant of the reaction by dividing the concentrations of the products and the concentration of the reactant. But the activity of pure solids is 1, which means that we can cancel the concentration of the barium sulfate in the expression because it is not needed to get the solubility product constant, thus giving us a solubility product expression of KSP is equal to the concentration of the barium ion multiplied by the concentration of the sulfate ion. Now, if one of the products of the reaction has a numerical coefficient, you must raise the concentration of that product to the power of the coefficient. Suppose we will dissolve another slightly soluble compound, magnesium fluoride, to an aqueous solution. Because 2 fluorine ions will result for every molecule of magnesium fluoride, we can write the KSP expression as shown. Since the ions came from the same solid, we can say that their coefficients in the equation is also the ratio of their concentrations. Hence, we can substitute the variable S to the concentration of the magnesium ion. We can also say that the concentration of the fluorine ion is 2S. Since the coefficient of the magnesium and fluorine is 1 and 2 respectively, the ratio of their concentrations is 1:2. The variable S also denotes the molar solubility for the magnesium fluoride. So when we are given that the KSB of magnesium fluoride is 6 times 10 raised to the negative 9, it will give us the final expression of KSP is equal to 4S cubed. To calculate for the molar solubility, we should divide the KSP by 4 and get the cube root of the quotient, which gives us the answer.
Now, if we add another salt that provides one of the ions of the slightly soluble compound, the reaction will be shifted backward because of the Le Chatelier principle, which states that if a stress is applied to a system at equilibrium, the system shifts in the direction that reduces the stress to move toward a new state of equilibrium. To simplify, the reaction will occur from the direction of the side with additional ions. And because there are more ions added to the solution, the molar solubility of the compound will be different.
Let's have an example. Magnesium fluoride is a slightly soluble compound. Given the KSP, we can solve for the molar solubility of the magnesium fluoride by applying what we have learned earlier. Suppose that 0.1 molar of sodium fluoride is added to the solution. Because sodium fluoride is a soluble ionic salt, it will dissolve completely to provide 0.1 molar of fluorine. To compute for the molar solubility of magnesium fluoride in 0.1 molar of sodium fluoride, we will add 0.1 to the concentration of the fluorine ions, which gives us KSP is equal to S multiplied by the quantity of 2S plus 0.1 squared. After you have multiplied those two together and transpose KSP to the other side, you will have a cubic equation, in which you can solve for the roots using your calculator. Once you have plugged in the values, you will have two roots. One is positive and the other one is usually negative. Obviously, the correct answer is the positive one. But in some cases, the two roots that you will get are both positive. If this scenario ever happens, you'll have to pick the root with the smaller value.